908 Grid Integration and Smart Charging Politics. Interconnection Storage. Grid interconnection and smart charging policies. Uncoordinated EV charging risks compounding concerns for grid operators to balance supply and demand, as well as placing additional pressure on networks. This could necessitate additional investment in peaking resources. The impacts can be difficult to manage, especially at very high EV stock penetrations and in systems with a peak grid. Coordinate smart charging of EVs offers the potential to help smooth increases in peak demand. Time of use tariffs can facilitate demand-side response by giving consumers price signals to shift EV charging to off-peak periods. An effective approach to minimize the needs for grid investment due to EV loads will be make network constraint known at a granular level, identifying areas that are under the most stress, including at the distribution system level. This allows smart charging to be tailored accordingly. Development of smart charging for EVs faces a number of challenges: lack of distribution grid transparency, network operation in medium and low voltage systems may not be able to forecast or have adequate data on real-time load at a geographically granular level. Aggregation and analysis of data from smart meters and the installation of distributed grid sensing equipment can help to overcome this barrier. Lack of demand response technologies on a large scale at the low level, technologies to send and receive detailed signals for individual load exist. However, their current application is limited to failed pilot projects and businesses. This reflects lack of a strong business case currently for these technologies. An inadequate market framework. The market design and regulatory framework in most countries does not provide a mechanism for constructing flexibility services between distribution system operation (DSOs) and consumers. Coordination between transmission system operators and DSOs needs to be strengthened to ensure coherence between the call for flexibility for local congestion and for system balancing. Smart grids that monitor load and control smart charging are being demonstrated in a number of countries, e.g., United States and Portugal. By the end of this decade, at least partial application of smart grid technologies is projected to help curb the need for investment in grid upgrades due to EV charging by ensuring that peak load events are avoided. In the longer term, as EVs account for more than one-third of the stock, smart grids will be necessary to avoid very high investment requirements. Eventually, the development of vehicle-to-grid technologies will enable vehicles to be plugged into smart chargers to contribute to balancing the system. In this manner, EVs will contribute to grid stability rather than being a source of instability to network balancing needs, and countries that fall in case 3A are more likely to require this technology. Smart charging for EVs offers new opportunities for power systems. Higher shares of variable renewables in the generation mix are contributing to the transition needed to meet decarbonization targets. Demand for electricity is increasing to power EVs, rising numbers of connected devices, improving the energy access, and a multitude of services. With rising demand comes the importance of power system flexibility, a smart infrastructure, and digital connectivity. New sources of flexibility can help to ensure that power systems are in balance at all times. The IEA projects that for the energy sector to reach net zero by 2050 globally, flexibility in the electric networks needs to quadruple in that period. EVs and their batteries could provide a huge reservoir of flexibility to facilitate the energy transition. There are three main types of smart charging. Off-peak charging uses simple signals such as a time of use tariff to incentivize users to charge during off-peak hours, or often there is a surplus of generation from renewables. Unidirectional managed charging. And charging time, rate, and duration are controlled and optimized by adapting to price signals and power system needs. It requires signals on grid and renewable supply availability to send by a power system operator or an aggregator. Third, bidirectional managed to or vehicle to grid V2G and charging for EVs that are technically able to input electricity into the grid. In this practice, EVs serve as distributed energy storage, dynamically charging at times when system availability is the highest and providing additional power supply when called upon. For all types of charging, optimization criteria are fundamental. Consumers can take advantage of flexibility options to manage their own consumption, match it with the output of their rooftop solar panel, and reduce the electricity bill if time of use tariffs are available. They may also be able to sell flexibility services to the wholesale and balancing markets of the power system. This can help to manage balance and peaking on the system. For example, it can offer local flexibility services to the DSO to smooth grid constraint through voltage support or congestion management. Of course, this is in addition to serving the charging needs of the consumer's EV. Markets and regulations must reward flexibility, ensuring that markets and regulations reflect the value of flexibility options for the system is a first step to boost smart EV charging adoption. Consumer-provided flexibility services will incur costs. For instance, in terms of battery deregulation, that must be approximately valued. This value can be reflected at every level of the power market. Cost-reflective, time-sensitive consumer tariffs will incentive drivers to charge their EV when it does not stress the network or when output from renewable is high. This helps to minimize the needs for costly network reinforcement. Smart charging can provide services around the power supply chain. Transmission system operator, peak capacity, balancing services, congestion management is distribution system operator, grid reinforcement, deferral, voltage support, and consumer retailer, portfolio optimization, energy cost saving, and reduced renewable curtailment. Open markets that include wholesale markets and those for flexibility services such as balancing, congestion management, and voltage control can provide tailored incentives by rewarding flexibility options where and when they have the most value. The higher the granularity of such price signals in time and space, the more value they bring to the system, but also the most complex they get. Consumers alone cannot be expected to deal with highly detailed signals or to navigate several layers of energy markets. This role can be undertaken by aggregators, either independent or utility subsidiaries that can contract with individual consumers to provide flexibility services and manage a pool of flexibility providers to maximize revenues and benefits to the participants and the system. Policymakers willing to harness smart charging flexibility potential can take measures to ensure their markets are adapted to distributed energy resources. One is to ensure that aggregators and, generally speaking, every type of distributed flexibility provider energy communities, peer-to-peer trading have access to markets on a level playing field based with traditional flexibility providers such as power plant or large industries. The most appropriate way to incorporate EV charging flexibility will vary depending on the power system and market specificities, but fundamentals such as the right of to participate, product specifications, rules for control, and flexibility measurement should be assessed to ensure that undue burden is not placed on the distributed flexibility providers. Regulations should leave room for business to develop innovative pricing solutions and business models that best fit both consumers and power system needs. Electric vehicle supply equipment development and charging management, a major condition for smart charging business development is the availability to control the charging of the large number of EVs. Interoperability allows aggregators to pool vehicle more easily and without burdensome procedures and interventions at consumer residences. This is key to smart charging development. Standards should be robust and cover cybersecurity, data accessibility, and minimum requirements that can be applicable for both private and public chargers. A few countries have all the elements required to roll out smart charging. That is country, and it is Japan. Yeah. Third, time of use tariff, peak or off-peak, night and day. They are proper hourly and ancillary services procured on the market basis. Flexibility service providers can participate in energy market. Smart charging policies or standards are enforced. Phased approach to building a smart charging strategy in the United Kingdom. As part of its goal to ban new ICE cars by 2030, effectively shifting to EVs and PHEVs, the United Kingdom took action to mandate smart EV chargers. The Automated and Electric Vehicle AEV Act 2018 mandates that all EV charge points sold and installed in the country have smart functionality and meet minimum device level requirements. The United Kingdom was an early adopter of a policy to mandate smart charger functionality. Others, such as France, has followed suit. Germany and Greece mandate smart charging for provide chargers to qualify for subsidies. Greece mandates smart charges for all public accessible charging points. Portugal mandates smart chargers at publicly accessible charging points. In July 2021, the UK government released its smart charging strategy that is based on the two-phase approach. This enabled policymakers to set out the framework in phase one, while providing visibility to stakeholders on the policy direction, yet having an opportunity to develop and adjust for more complex topics that will be addressed in phase two. Phase one requires a new charge point, public or private, be smart chargers and be set by default to charge only at off-peak times of the electricity system. Smart functionality is defined at the device level and includes the ability to send and receive information, to modify the time of charging in response to information received, and to use the functions to provide demand response services. It also incorporates basic cybersecurity standards, existing cybersecurity standard ETSI EN 303645, basic interoperability to ensure that charge points are not designed to block change of supplier, and data accessibility, including customer access to consumption data. The specification outlined In the regulations for EV smart charge points that come into force in June 2022, Phase 2 topics include full charge point operator interoperability, the ability of consumers to switch operators, and more in-depth analysis of elements such as cybersecurity and